Numpy Correlate is not providing an offset. I am trying to look at astronomical spectra using Python, and I'm using Numpy.correlate to try and find a radial velocity shift. I'm comparing each spectrum I have to one template spectrum. The problem that I'm encountering is that, no matter which spectra I use, Numpy.correlate states that the maximal value of the correlation function occurs with a shift of 0 pixels, i.e. the spectra already line up, which is very clearly not true. Here is some of the relevant code. The output of this code is shown here. What I have. Note that the cross-correlation function peaks at an offset of 0 pixels despite the template, blue, and observed, red, spectra clearly showing an offset. What I would expect to see would be something a bit like, albeit not exactly like, this is merely the closest representation I could produce. What I want. Here I have introduced an artificial offset of 50 pixels in the template data, and they more or less line up now. What I would like is, for a case like this, for a peak to appear at an offset of 50 pixels rather than at 0. I don't care if the spectra at the bottom appear lined up, that is merely for visual representation. However, despite several hours of work and research online, I can't find someone who even describes this problem, let alone a solution. I've attempted to use Numpy Correlate and MATLAB's SCA, and bots show this same thing, although I'm led to believe that they are essentially the same function. Why is the cross-correlation not acting the way I expect, and how do I get it to act in a useful way?
The issue you're experiencing is probably because your spectra are not zero-centered. Their RMS value looks to be about 100 in whichever units you're plotting, instead of 0. The reason this is an issue is because Numpy.correlate works by sliding imag_data over temp_data to get their dot product at each possible offset between the two series. See the Wikipedia on cross-correlation to understand the operation itself. When using mode equals same to produce an output that is the same length as your first input, temp_data, Numpy has to pad a bunch of dummy values zeros to the ends of imag_data in order to be able to calculate the dot products of all the shifted versions of the imag_data. When we have any non-zero offset between the spectra, some of the values in temp_data are being multiplied by those dummy zero padding values instead of the values in image_data. If the values in the spectra were centered around 0, RMS equals 0, then this zero padding would not impact our expectation of the dot product, but because these spectra have RMS values around 100 units, that dot product, our correlation, is largest when we lay the two spectra on top of one another with no offset. Notice that your cross-correlation result looks like a triangular pulse, which is what you might expect from the cross-correlation of two square pulses, CF convolution of a rectangular pulse with itself. That's because your spectra, once padded, look like a step function from 0 up to a pulse of slightly noisy values around 100. You can try convolving with mode equals full to see the entire response of the two spectra you're correlating, or, notice that with mode equals valid that you should only get one value in return, since your two spectra are the exact same length, so there is only one offset, 0, where you can entirely line them up. To sidestep this issue, you can try either subtracting away the RMS value of the spectra so that they are zero-centered, or manually padding the beginning and end of imag_data with lim_temp_data/2:1, dummy values equal to np.sqrt np.mean imag_data2. Edit. In response to your questions in the comments, I thought I'd include a graphic to make the point I'm trying to describe a little clearer. Say we have two vectors of values, not entirely unlike your spectra, each with some large non-zero mean. F has a spike around t equals 90, and G has a spike around t equals 180. So we expect the correlation of G and F to have a spike around a lag of 90 time steps. In the case of spectra, frequency bends instead of time steps. But in order to get an output that is the same shape as our inputs, as in Numpy.correlate G, F, mode equals same, we have to pad F on either side with half its length in dummy values. Numpy.correlate pads with zeros. If we don't pad F, as in Numpy.correlate G, F, mode equals valid, we will only get one value in return, the correlation with zero offset, because F and G are the same length, and there is no room to shift one of the signals relative to the other. When you calculate the correlation of G and F after that padding, you find that it peaks when the non-zero portion of signals aligns completely, that is, when there is no offset between the original F and G. This is because the RMS value of the signals is so much higher than zero. The size of the overlap of F and G depends much more strongly on the number of elements overlapping at this high RMS level than on the relatively small fluctuations each function has around it. We can remove this large contribution to the correlation by subtracting the RMS level from each series. In the graph below, the gray line on the right shows the cross-correlation the two series before zero centering, and the teal line shows the cross-correlation after. The gray line is, like your first attempt, triangular with the overlap of the two non-zero signals. The teal line better reflects the correlation between the fluctuation of the two signals, as we desired.
If you want to see more, please consider subscribing.